First of all, I want to thank the workshop organizers for inviting me. Today, I'm going to talk about some of the recent work in my lab on fine-grained and multi-label zero-shot learning, whose goal is to recognize and learn more labels without necessarily having samples and data annotations. Motivation for this work is basically to take deep neural networks and make them applicable to more challenging real-world tasks. Today, we are closer to the vision of involving AI in our daily life, thanks to advances in deep neural networks in different fields, whether it is self-driving cars that are able to navigate more safely in the environment because of more accurate models of detection, recognition, and semantic segmentation, or whether it's in robotics where we are able to learn more effective policies from simulation data, demonstrations, and videos. And similarly in security, where we have more robust and accurate authentication methods thanks to advances in face and biometric recognition. Now, the success of DNNs heavily relies on having large amounts of annotated data and training samples, often requiring hundreds or thousands of samples for every class in order to learn effective recognition models. As a result, current methods are able to well recognize typical classes of objects and scenes for which there are many training samples available. This means that current systems are able to well recognize, roughly speaking, hundreds or a few hundreds of different classes. Now, when it comes to practice, there is a large number of classes that have only a handful of training samples. Why? Because the number of objects and scenes is very large. Some of them are rare, meaning that it is not easy to gather samples for them. Also, annotation is a costly process that requires annotators to carefully observe data and label them. So this long distribution tail of annotation then hinders DNNs from effectively learning many classes. The problem is even more pronounced when we consider a space of unseen labels, classes that don't have any training samples, again, due to difficulty of gathering annotations, or simply because as systems operate in real world and become expert in some concepts, then they need to expand their knowledge to new concepts. And in other words, the space of unseen labels often keeps expanding in time. So the question is, how can we learn DNNs that can detect and recognize things that they haven't seen yet? So today I'm going to focus on two challenging scenarios of training DNNs with basically no samples. One is the problem of multi-label recognition. In the problem of multi-label recognition, unlike the multi-class problem, we have an image and our goal is to find all labels that exist in the image. For instance, in the image on the left-hand side, we want to find that there is a street sign, there is a car, there are people, there is a person with a backpack, and there is a road and a street in the scene. As a result, there are thousands or tens of thousands of possible labels that we want to identify and recognize and have very accurate models for. Many of these labels then are going to have few or no training samples, and that's a challenge. And another challenge is the fact that many of these labels also are going to have missing annotations. For instance, the labels that I've shown by red in these images are the ones that haven't been labeled by annotators, and they're missing in the annotations. So the question is then, how can we recognize all seen and unseen labels in an image in this multi-label setting? And that leads to the problem of multi-label zero-shot learning that I'm going to focus on. The second problem that I'm going to talk about is the problem of fine-grained recognition in the zero-shot setting again. In the fine-grained recognition problem, classes are visually very similar to each other. Often we need experts to sit and annotate data to distinguish between different classes. And this is going to be also very costly. Images of different clothing and fashion types is one example of this, where different clothing types could be very close or visually very similar and be slightly different in some few attributes. Or the problem of finding and recognizing different bird species or animal species is another example of fine-grained classification where classes are very visually similar. So the next question that I'm going to talk about today is how can we recognize these unseen fine-grained classes? And that leads to the problem of fine-grained zero-shot learning. This talk is going then to focus on these two problems of recognition and localization of classes or labels in the multi-label and fine-grained settings in the zero-shot learning framework, where we don't have training samples for many of these fine-grained or multi-class or multi-label problems. I'm going to talk about different methods based on multi-attention mechanisms that are able to learn and transfer knowledge from seen to unseen labels. And also I'm going to talk about compositional learning methods that can recognize complex concepts and complex structures by decomposing them as superposition and composition of more rudimentary components that then can be combined and recognize more complex and abstract concepts. And I'm going to show that these methods are going to significantly improve the state of the art on really large data sets as well as the standard benchmarks. So let's start by looking at what the state of the art in the space of zero-shot learning is. In order to be able to transfer some knowledge from classes that have training samples to classes that don't have any training samples, we need to find some common ground between different classes. And that's often characterized through the so-called class semantic vectors. These class semantics are going to be consist of different types of different attributes that are going to characterize a class. For instance, in the case of different clothing types, we are going to have multiple attributes, whether, for instance, the texture or material is destroyed, whether the fit is slim, whether it has pocket, whether the material is soft or not. And for each of the classes, then we can give some score or just indicate presence or absence of the attribute in the class. And this is going to be the key that allows us to transfer knowledge. Or in the case of bird species, it can be, the attributes are going to be different. For instance, whether the belly or wing or bill of a bird has a particular pattern or a particular color, and we can then build these semantic vectors for each of the classes. Then there are two types of methods for zero-shot learning. One are basically the discriminative models, and the other are the class of generative models. The discriminative models are going to find a joint embedding space between visual data and class semantics that then allows generalization to unseen classes. So what we do is to take an image and pass it through a network and extract a feature vector for the image, which I'm going to show it here by F. Then we take a semantic vector of the class. That's assume that that's the correct and the ground truth semantic vector, which is Z, and we are going to pass it again through some network and extract some representation GZ. And for the correct class associated to an image, we want to find embedding, a joint embedding space that is going to bring these two close to each other. And on the other hand, for an incorrect class, we want to embed the associated representation of the semantic vector of a wrong class to be sufficiently far from the image feature. And as a result, what we do is to design and minimize this ranking loss that is going to enforce that the similarity, or in this case is going to be the simple inner product between the image feature and the representation of the semantic vector for the correct class should give a higher score or higher value than incorrect class, and it should be larger by some margin delta. The second class of zero-shot learning are basically the class of generative models. In the case of generative models, what we do is to learn conditional GANs, conditional generative adversarial nets, that are going to get an image and that are going to get a noise vector as well as be conditioned on the semantic vector of a class and learn to generate samples from each class. Now that they have been trained on the seen classes, we can then give a semantic vector of an unseen class, and we are able to generate features of unseen classes. And once we generate features of unseen classes, we are going to pull them together with the features of classes that have training samples and train a conventional and a standard classifier. And that's going to be the structure of generative models. So independent of whether we are going to look at discriminative or generative, there are some challenges in the existing state of the art that limits their applicability to especially fine-grained problems and multi-label problems. They often, these methods often rely on holistic features that look at the image in its entirety, and they lack fine-grained details that is often needed in order to discriminate between different classes. These features are also, it's also very challenging and hasn't been well understood how we can generalize these methods to handle the problem of multi-label recognition, where we want to find all labels, but in an efficient manner in both computationally and memory-wise and performance perspective. And that's basically what I'm going to talk about today. So let me start then with the problem of multi-label zero-shot learning, and I'm going to talk about the new method based on a shared multi-attention mechanism that is going to handle the problem effectively. So in the case of multi-label zero-shot learning, we have an image and we want to find all its labels. Some of these labels are seen and some of them are unseen. For instance, in this image that I have shown here, the set of seen labels are sort of arc, stone, and travel, and then there are some unseen labels that, for instance, in this case, it would be steps, door, and person that aren't don't have any training samples. So CS denotes C sub S denotes the set of seen labels, and C sub U denotes the set of unseen labels. So we are given then a training data set of images and what set of labels are present in the image. I denotes an image and Y denotes the set of labels in the image. And the goal is going to be to basically find all labels. And what we want to do is to leverage these class semantic vectors. We want to use the semantic vectors of the classes, both seen and unseen, in order to transfer knowledge and be able to recognize in an image all its labels, whether some of them are seen and whether some of them are unseen. So the challenge is basically, as I said earlier, we have things like 10,000 possible labels to classify, and the question would be, how can we efficiently learn methods and models for this large number of labels? And the other challenge is we want to be able to find out basically the regions in images that are being associated with each of the labels without having necessarily these bounding boxes. That is going to be super costly. As I've shown in this image, all we have is basically a list of labels that appear in image in our training set, and we don't know where each label appears. So then one really promising approach is to use attention models that are able to localize labels and concepts. So we can go through two extreme and take two extreme scenarios. One extreme scenario would be to learn a single attention model for classifying all labels, whether they are seen or unseen. And that has some challenge, a big challenge, that given the fact that we are asking one attention model to recognize thousands or tens of thousands of labels that have large appearance variations, it's going to be really difficult for one attention to capture this diversity. And it's going, as I've shown here in this figure, it's going to fail and only will recognize maybe a few of the labels. The other extreme would be, okay, instead of using one label that recognizes, one attention that recognizes all labels, then what we can do is to have one specialized attention model for every possible label. So what we are going to do is to have one attention that is specialized, for instance, in recognizing arc, another recognizing stone, etc. But there are, again, challenges here. How can we actually learn these attentions then for specialized attentions for classes that we don't have any training samples? So that's one challenge. The other is that having a specialized attention then is going to be super costly, and we need to, and it's going to have a huge computation and memory cost to have basically one attention per label when we have thousands or tens of thousands of labels. So the method then that we propose is basically being somewhere in between these two extreme scenarios. So we are proposing to use a shared attention mechanism where we take and design M attention modules. M is bigger than 1, but it's much smaller than L, so that it's going to be computational and memory-wise efficient. And each of these attentions is going to be label agnostic and is going to be become an expert automatically in recognizing a subset of labels that are generally ideally more related to each other. And this notion of sharing is what allows us to transfer knowledge from seen labels to unseen labels, given their similarities. So as I said, each attention then becomes an expert in some related labels that are going to be picked automatically with the learning methods that we propose. And the other cool thing is that the complexity of each label, the visual variance of each label characterizes then how many attention modules we are going to use to effectively represent that label. So for instance, in this figure, the attention 1 is going to be specialized in recognizing arc, stone, and steps, and then the second attention is going to be expert in recognizing travel, person, outdoor, which are each group are more semantically related to each other. So what we do then is to basically take an image, divide it into R different regions, apply a standard network CNN to each region, and extract these R different features, F1, F2, FR, from each of the regions. Then these feature of the regions are going to be given to each of our M attention modules, and these attention modules then they are going to learn to focus on a different part of an image. The attention weights are these. For the attention 1 is alpha 1, which is a vector of R values, and for the M's module is going to be alpha M. And using that, we can build these attention features, which are H1 up to HM. Now, what we want to do is to find a joint semantic space that each label is going to be recognized by the closest and more suitable attention feature. And as a result, what we propose is to compute the score by taking the maximum of the inner product between the attention features and the representation and transformation of the class semantic vector when we are maximizing overall the attention modules. And this then allows us that each label and each class to be classified and recognized and localized by possibly an appropriate and a different attention module. So then if we simply minimize the ranking loss, this is going to lead to some ill-posed solutions. What we want to do is to prevent overfitting and some trivial solutions. So one of the issues that we can face is that different attention modules could possibly look at the same region, which is not ideal. So what we want to have is that these different attentions are going to be expert in different labels. So what we then propose is a diversity loss that says that these attention maps should pay attention to different regions in an image. The second loss or second constraint that we enforce is that the attention features that we are going to extract should do better than basically a naive feature, which would be simply take an average of all the region's features. So we want to do better than simply than basically ignoring the attention. And ignoring attention can be characterized by the score S bar O, and is always basically the score of the attention. And we want to have a better score for the classes that are present using the attention features. And for this, we are going to design the so-called relevance loss. Another possible challenge would be that given the fact that we have more than one attention, in learning, we could face the issue of multiple attentions collapse and several attentions don't be used at all. So what we want to do is to make sure that every attention is basically effectively utilized. And what we do is to measure the utility of each attention module M, which we are denoting it by L sub M, which basically counts how many labels are going to be represented by attention module M. And what we want to then enforce is that every attention module should have a non-zero utility and effectively sufficient utility. And for that, then we are going to minimize the sum of the squares of these utilities. And we call the associated loss distribution loss. So at the end of the day, we have a standard ranking loss plus these different diversity, relevance, and distribution loss to be optimized simultaneously over the attention module parameters and the embedding and the joint embedding space parameters. So for the experiments, what we have done is to look at two different data sets. One is the NUS-wide data set that has around 160 training samples from about 900 seen and 80 unseen classes or labels. And the other is the Open Images dataset, which is a very large scale dataset, has 9 million training images, around 7,000 seen classes labels, and 400 unseen labels. And this is more challenging dataset to deal with. The number of labels per image is in this case 8.4 compared to 5.9 for NUS-wide. So we look at two different evaluation metrics. One is the mean average precision, which basically is a retrieval measure, which measures the accuracy of the rank images for each label in our retrieval. And then we also look at the F1 at K, which measures when we retrieve the top K labels, how accurate those rank labels are for each image. So these are complementary metrics that that are going to give us complementary information about performance. So one setting of the experiments that we have performed is the zero-shot learning. In the standard zero-shot learning, we assume that in the zero-shot setting, we assume that the test samples are from just unseen classes. And as I've shown here, we are able to do really well on improving both the F1 and MAP score on both datasets, particularly for NUS-wide, by something more than 3.8% on F1 or 4.3% on the MAP. And even the performance on Open Image is significant because we have 5,000 labels, 7,000 labels that need to be identified, and the accumulated improvement is significant. One thing that you can notice from this result is that the performances in the F1 score are lower in the case of Open Images than NUS-wide, and that's because of much larger number of labels that should be retrieved. So the other setting that we have experimented is the generalized zero-shot learning. In the generalized zero-shot learning, we assume that test samples come from both seen and unseen classes or unseen labels. And again, we see a similar trend in our method that for this more challenging setting, there we need to identify and distinguish between seen and unseen classes. We do well on NUS wide, and we get basically 2.9% improvement on F1 and 1.9% on the map score, and similarly for open images. Given the fact that we are using an attention model, then one thing that we investigated was how accurate this attention model is in terms of localization. And what we measured was that if the maximum attention is going to be inside the ground truth bounding box of a label, then we are going to count it as a correct localization. And here, in these three set of bar charts, I have shown the two extremes, where in the left, we are using one attention per label. In the middle, I've shown one attention for all labels, and in the right-hand side, I've shown our shared attention model. And as I discussed earlier, when we learn one attention per label, we are able to do well on the seen labels. But we are going to do poorly on the unseen labels because it's not going to have generalization power. On the other hand, when we use one attention for all labels, we are not going to do really well on basically seen labels, but it's going to do a slight better on the unseen labels because it has better generalization power. And on the other hand, when we look at our method, shared attention, we do both well on the seen and unseen, and as a result, we get the best harmonic mean, which is really the important metric we care about, the harmonic mean between the seen and unseen accuracy. Here in this bottom bar chart, I have shown the top 20 and the bottom 20 classes for which the localization score improves the most or degrades the most. And as you can see, there are many of these labels. On the left-hand side, their localization performance significantly improves by more than 15 or 10% in the map score. And these are sort of labels that are less varied, like drawer or coffee cup. And then there are some labels that their performance basically degrades compared to using one attention per label. And these are labels that have more variations, much more variations than could be handled by using few attentions. One thing that I mentioned in the beginning is that this method that we have proposed has the ability to automatically assign the appropriate number of attentions to each label. And here I have shown the labels of the NUS wide, and basically I have the utility of these attention modules. So as you can see on the left-hand side, we have labels that are going to use very few, or basically one attention module, and those are labels like a straight house and cars that have much less visual variance, visual appearance variation. And as we move toward the right, we will see labels get more complex, and they have more visual appearance variation, and they're going to use more and more attention modules. So these are going to be automatically assigned by the method itself. And here I've shown some of the results on the visualization of two of the attention modules for these four sample images, where, for instance, for the image of a leopard in the bottom left, we can see that the one attention module is able to successfully focus on the seen label of leopard and predict the unseen label of animal. And on the right-hand side, it's going to focus successfully on the label of tree. And it's going to also successfully localize the associated regions in the image. So having talked about the multi-label zero-shot learning, I'm going to switch to the other problem, which is fine-grained zero-shot learning. And I'm going to talk about the method based on compositional learning and dense attention in order to address the problem. So in the fine-grained learning problem, we have classes that are visually very similar. And by visual similarity, I mean that they are going to be distinct in only few attributes. So, for instance, these three images that are from three different classes, they are really distinct in only two attributes with respect to each other. And that's what makes the problem challenging. Some of these classes are now seen, and some of these classes are not seen. And the question would be how we can recognize at the test time seen and unseen classes. So what we do is to then, similar to before, get a training data set of images and their associated class. So notice that here there's only one class. And we assume that there is only one class in each image, unlike the previous part that I showed. We have seen classes that have training samples, and CU, which is the unseen classes that don't have any training annotations. And what we assume is that we have the semantic vectors of the classes. So ZC denotes the semantic vector of class C. And what we also assume is that each of these semantic, so each of these attributes, ZC1, ZCA, are going to be also accompanied with the semantic vector of the attribute. So for instance, for the first attribute, which is belly pattern stripe, then we have some word-to-vec representation of this attribute, which we are denoting by V1. And for the last attribute A, which is belly color white, then we have VA, which is its word-to-vec of this description. So the idea that we propose and we use in order to address the problem is basically based on a compositional learning and an attribute-based decomposition of the problem. So as I said, the key observation and insight that we have is that these classes are distinct in only very few attributes. So then what we want to do is to localize regions in each image associated with each attribute and use that information in order to now leverage the semantic vectors of classes to figure out what sort of attributes are present and absent, and based on that we figure out which classes are is in the image. So this compositional model that then we propose is basically based on what we call a dense attention model, that we are going to have one semantically guided attention model corresponding to each attribute. So for attribute 1, we are going to have attention module 1 that is going to be guided by the semantic vector of the attribute 1B1, and it's going to extract the attention feature H1, and similarly for every other attribute. So we are going to extract different attribute features, and we call them dense features because we have lots of attributes and we have lots of attention features. Then what we do is to try to find an embedding space where instead of finding a joint embedding between a holistic feature representation and the whole semantic vector, now instead we are trying to find embedding and a joint embedding space between each attribute feature and the semantic vector of the attributes. So we are going to basically find alignment at the attribute level instead of the holistic and whole image level. And the goal would be basically to align each attribute with the associated semantic vector. And this embedding is going to produce us some scores, which we are going to call E1, E2 up to EA, corresponding to the A attributes. This is simply the inner product between these attribute features, attribute attention features, and the representation or transformation of the attribute semantics. So then once we have computed these scores of each attributes, its presence or absence, then we compare it with the semantic vector of the class by taking simply the inner product between the two to compute whether that class is present in the image or not. There is a caveat here that we are now treating all attributes equally. And as I mentioned in 2 slides earlier, different attributes have different weights because some of them are going to be discriminatory and have discriminative information, like the ones that are sort of flipped, and they're going to be the ones that are going to say whether some class is present in an image or not. So the solution then would be when we want to upweight these discriminative attributes and downweight the non-discriminative ones. So in order to do that, we propose this sort of another weighting mechanism, which could be also thought as an attention, that computes the contribution of each of these attributes by some values or scores that are beta, that are going to be between 0 and 1. And these betas now are going to modulate the score of each attribute in order to compute the class score of a class. And once we have these scores, then we are going to give them basically to a standard ranking loss or a cross-entropy loss to train the system over the parameters of the attention and embedding model and the attribute contribution modules. So we have done some experiments on cup data set, animal with attribute, and sun data set, and these are different fine-grained classes and data sets. And here I've shown the accuracy on seen and unseen labels, as well as the harmonic mean between the seen and unseen accuracy. The first group of methods are basically methods that use that are discriminative and use holistic features, and the second group of methods in the table are generative models, and the last one, DAZZLE, is dense attribute-based zero-shot learning, which is our method that uses these, instead of holistic features, dense attentions. And we show that basically this significantly improves the performance on two of these data sets, cup and animal with attributes, by a significant margin. However, on the sun data set, we don't do as well, and that comes from the fact that sun has less than 20 samples per class, which is going to be insufficient for training this dense attention model, and that's really the place that it hurts the method. The interesting thing is that now we have localization of these different attributes, and we have interpretability of the results, and we can find evidence for also absent attributes. So for instance, for the image on the top row, then the attention mechanism is going to successfully focus in region associated with each attribute, whether that's head pattern plane is going to successfully focus on a head, or primary color black is going to successfully focus on the bird, or if you look at the right hand side, for the attribute which is head pattern crested or belly color white, is going to successfully focus on those regions, but it's going to produce a large negative scores that show that these attributes are absent in the image. Another interesting thing is that we are able also to, given the fact that we are working with the semantics of the attributes, we can also fine-tune and modify the semantic attributes in our end-to-end learning setting. And this helps us to get a better attribute embedding space. So the green circles here are the semantics of the attributes before refinement by our method, and the blue ones are the ones that we got after refinement. And if you look at the bottom left, then what we see is that the attributes that were sufficiently far in the original space now are going to be closer, and those are things that are related, like hunter and agility and fast and lean. And on the top right-hand side, we have attributes of inactive and slow that were originally far, but now are going to be close to each other in the embedding space. So having said that, then this method was really a discriminative method for zero-shot learning. What we wanted to do is, given the success of generative model, the next step that we took was basically try to generalize it to the generative model as well, to the generative setting. Really the key for the success of the previous method was being able to generate these attribute-based features and attribute-based localization, or dense features, in order to train a classifier. So what we are also here observing is that we don't want to get holistic features that are not going to be capturing enough information, discriminative information about fine-grained classes. So what we propose instead is to generate dense features or attribute-based features for unseen classes. And once we are able to generate these attribute-based features for also unseen classes, we can then pull them together with the seen features and basically train a standard discriminative model, which is our previous method now on both seen and unseen classes. So the key idea here is basically to make the observation that if we are looking for some features of unseen classes, we are really maximizing the probability of these dense features given the class and the semantic vector of the class. And that's our generative model. So we are going to use the base rule, and we are going to turn this overhead and say that, okay, this is equivalent to finding the best features that are going to maximize the probability of a class given the dense features and its semantic vector times the probability of dense features given the semantic vector. The first term on the right-hand side is basically the discriminative model, which is basically the method that I showed in the previous case. That's Dazzle. The right-hand side, the probability on the very right-hand side, H given Z, is our prior. And we need to come up with a prior and then maximize this probability. The challenge here is that this maximization is really combinatorial because there are lots of possible H's and the space of H is extraordinarily large. So how can we do this search efficiently? And the way that we address it is through a sequence of steps. One thing that we propose is that instead of searching in the entire space of dense features, we are going to look at only possible combinations of attribute features of the training samples. And for the prior, and this is going to restrict our search space, but it still is going to keep the search into a combinatorial regime. The other would be then we are going to make it more tractable by building this prior distribution in an efficient fashion, in a tractable fashion, that we are going to find the most semantically related samples to a given class through some sparse optimization, and then we are going to assume some independence over this distribution of dense features that is going to break down into product of independent of features of each of the features. And through an appropriate probability that is defined, and this is going to lead us to a tractable optimization and a search. So at the end of the day, what we do is basically we sample from this prior that we build and get our features from the unseen samples by maximizing the product of these two probabilities. And once we have the features of unseen classes, then we train our Dazzle that I showed in the previous part. And here I've shown the accuracy on seen and unseen and harmonic mean over animal with attributes cow and sun, as well as a deep fashion dataset. So as you can see, in 3 out of the 4 categories, we do really well, and even do much better than Dazzle, thanks to the generative model. On sun, again, the same problem is going to persist because this is going to use Dazzle as its backbone. So since we don't have enough samples of seen classes, this is not going to do, Dazzle isn't going to do well. So this generative also isn't going to do as well. One thing that here we did was we really decided to do something more than just, a standard, these benchmarks. And we thought that it's really good for the community also to look at, more challenging and more interesting data sets. And we look at the deep fashion data set that has basically is pretty challenging, is large, 1,000 attributes from 30 seen and 10 unseen classes that we trained. And we showed that actually there is a significant improvement in performance on the deep fashion as well. And one cool thing about this is that the generated features are interpretable, given the fact that we are going to be able to pick scene classes and pick which part of the scene classes are going to be used for composition of features, then we have interpretable results. So for instance, for the image on the left-hand side, which is from an unseen class, then we are going to select the head color blue from the first training image, wing pattern stripe from the second image, and under tail color gray from the third image, and their associated attribute features, and they are going to pull them together to build a dense feature for this image on the left-hand side. That leads to sort of both localization and interpretation of the results. So, okay, so to summarize, basically I talked about the problem of fine-grained and multi-label zero-shot learning. I talked about multi-attention mechanism and compositional learning in order to address these problems. And one key point was how we can build these shared attention models that can transfer knowledge to unseen labels. And they significantly reduce the memory and computational cost. And the other was how we can actually build these dense attentions and use them in discriminative or generative fashion by composing these attribute features in order to classify and distinguish fine-grained classes. So the papers that I presented are basically these 4 papers that I have listed here. We also have the codes of these methods that are available on my website, and through this link you can access the code, and you can basically build on them and try them. So with that, I'm going to thank you and also, again, the organizers.
Okay, so I want to use this chance to thank the speaker and the audience, and then I would like to ask the audience if you have any questions regarding this talk, because the speakers, Professor El-Mafar, is online with us right now. So if you have any question, please speak up.
So this is Terry Bolt. I have a question for you. So in looking at the unseen categories, there's a section of work that I do that's related to OpenSet and the detection of unknowns. Have you tried to apply any of your ideas to actually deciding this is something that is unknown versus it's something I'm going to try and do zero-shot learning? Because zero-shot learning, you're told what to look for. Here, you would have no idea what you're looking for.
Yeah, that's a very good question. Can you hear me?
Yes.
Yes.
Okay. So I think that's a very interesting question. We have not looked at the setting of whether figuring out whether something is sort of we don't know what it is, or basically in the case of zero-shot learning, we are assuming that we are given basically the semantics of the classes, which are either seen or unseen. So we assume some knowledge and some information about even the things that we have not seen. And what you were asking is that what if we, try to generalize it to the setting that, we can recognize whether something is even in our set of semantics, whether the semantics of seen or are seen or not. And that's something that I think is a very interesting question to look at. I think it's very interesting. We haven't looked at it. However, I want to emphasize also that one possibility of addressing the problem could be through basically the class uncertainties and probabilities. If the current semantics that we have, we are not able to produce reasonable confident results in our outputs, then perhaps we can filter it out and sort of say that, okay, this makes sense. It makes sense to assume that this class is not in the set of our sort of is not in our current knowledge base. So it's something that we haven't encountered yet.
Thank you. And sort of related, in fact, to your second part of the answer, how do you handle, right now your semantics assume effectively perfect knowledge, not that I think it might have this property. How would you handle uncertainty in the description of the unknown object? or unseen object?
Right. So that's also another very interesting question. So I somehow simplified the representation of the semantics into these kind of 0 and 1s for simplicity of the presentation. One thing that we can certainly do, and for some of these data set is actually the case, is that each image, for instance, can have its own sort of attribute or semantic vector, which could be distinct from other classes, and that produces some sort of a overall uncertainty of the one single, with respect to having a single semantic vector that describes the class, instead of a single vector that this is basically a global representation of the class. In some cases, we have basically multiple possibilities, several possibilities that those can represent the class, and that itself produces some sort of as you can imagine, some sort of distribution over the semantics, which incorporates some mean and variance, and that's something that we can also deal with at the image level. The question, in a sense, we can deal it with by finding a joint representation where we are basically mapping the semantic of each image with close to the representation of the image. So to some extent, this can deal with it, but I agree with you that if we are assuming that, this is maybe my semantic vector, which is just a global vector, and then we have these sort of uncertainty bounds, variances, for instance, on each entry, the question would be how we can actually address the problem. And we need to somehow, in my opinion, incorporate this notion of uncertainties into our sort of ranking loss and the loss functions that we are designing, so that the embedding space that is going to be found is going to take into account the level of uncertainties in the description of each of the classes.
Thanks.
Right. Thank you so much. And for the sake of the time, so I encourage if other audience have any other questions, please contact Professor Elmafar offline. And thanks again for this talk. And then the next talk is given by Professor Jinsong Yuan from University of Buffalo Sunny. So I'm going to play the video now.
Hello, everyone. Welcome to this workshop. Before I start, I would like to thank the organizers for the invitation, and it's my great pleasure to give a talk of visual learning with less label data today. I'm Jinsong Yuan from University at Buffalo. So computer vision is to compute what is where by looking. During the past few years, we have seen very promising applications of computer vision, from autonomous driving, human pose estimation and tracking, image retrieval, video understanding, so on and so forth. Okay, most of those success, if we look back, we may say during the past few years, one of the major forces to push the performance is through the machine learning model, especially deep learning. Okay, more and more computer vision problems have been formulated as a learning problem, for example, through typical supervised learning. So here, X, X is the image, Y is the annotation of the image, or the information we want to get from the image. If it is object detection, what can be bounding boxes? If it is object recognition, I will be the category of the image X, and so on and so forth. And Y can also be image. For example, if X is the video, Y is the optic flow, then both X and Y are two-dimensional matrices. Okay. And the learning goal is by providing training data. Well, every training data has two parts. One is X, again, is the image or the video, and Y is the annotation of the image. And the goal of the learning is to learn a mapping F from X to Y, so that next time you input a new image X, I can return, but after learning the mapping function f, I can learn the output, or to predict the output y from the given x. Okay. How to make visual learning successful? Okay. During the past few years, people tended to believe that the data, especially supervised training data, is the key. Okay. In general, we see in terms of results of the deep learning models for vision applications, we see in general more data will bring us better performance. And in some scenarios, applications, data is indeed become a barrier that differentiate, for example, big companies and the small ones. Well, those big companies usually has better access to big data. Okay, that's why in the extreme case, some people start to believe that the data is the key in the battlefield and is the key differentiator that can make your application or the learned model success. Well, I would say it's not just the data, but more specifically, what we would say is the labeled data. Okay, labeled data means you should have the feed into the deep learning model. You should have both X, which is the image data, for example, and also Y, which is the annotation of the data, which tell the machine the meaning of the input data X by providing the annotation Y. Okay. So in all those scenarios, okay, we actually put the data as the teacher. Meaning, in order to teach a machine to perform visual tasks, computer vision tasks, we feed the machine with a lot of training data with both X and Y. Again, data and the annotation of the data, images and the bounding boxes, for example. If it's in this particular example, is for example, if you want to do object detection, then there were already companies that can provide services for the data annotation, right? You can pay the company, provide them the data. If you do not have annotations, then you can pay the company and buy the annotations Y, while given the X. Okay, so and once you have enough pairs of X and Y, then you can start to train your model, and with more and more data, annotate the data provided to your model through the deep learning process, then hopefully better and better performance we can achieve. Okay. However, labeled data in many real applications are not as easy as we thought that can obtain. For example, labeled data could be expensive. You have to pay others to annotate the data for you. Okay, if you cannot do it by yourself, and no matter how much data you obtain, annotated data you obtain, the model may still feel it's not enough. You may still want to collect more data to help you to tune the model with better and better performance. Okay. Also, in some other scenarios, for example, if you talk about the medical applications, medical image applications, the annotated data may not be easy to acquire. The data is limited, and especially the annotation of the data. Okay. Also, in other certain situations, the data could be incomplete. Incomplete could be I only have the X, but I missed the Y, or I have X, I have part of the Y, the annotations, but it's not completely annotated. The annotation could be noisy as well. Even though you pay others to do the annotation job for you, or even you do the annotation by yourself, there's no guarantee the annotation is 100% reliable. Okay, if that happened, that means your training data is going to contain noise, and your model, your learning model, has to deal with that. And also more recently, people realize even the data annotation is correct, it does not mean it will not be unbiased. Okay, I will give you some other examples of what the bias-style annotation mean. But here, the general meaning is that if I give you the same image, if I'm asking 2 people or 3 different people to annotate the image, they may give me slightly different or even sometimes very much different annotations, depending on the computer vision applications you ask them to annotate. Okay, so data as the teacher may not be as easy as we thought. Okay, there's a lot of different. The teacher itself may have its limitation, may have its own problems, and we need help. Okay, so today I mainly want to share the recent progress of visual learning with less labeled data. Okay, in case we have, because again, labeled data, annotated data are not easy to obtain. Okay, so as we discussed in the previous slide, so now the question is that what if we do not have enough labeled data? Is it still possible for us to perform visual learning and make our computer vision applications to be successful? Okay, so in the following 40 minutes, I will mainly share with the 3 aspects of visual learning. First is visual learning with synthetic data. Okay, they are not real data, but still can help with the real applications. And the second, I will talk about the visual learning with weak labeled data. The data is not completely labeled. The true annotation is missing, but some extra annotations are there which could be helpful. Okay, and thirdly, we will briefly talk about visual learning with pre-trained models. Those models which have been pre-trained using millions of the images, how it can benefit our future or other applications. The first thing, visual learning with synthetic data. I'm going to start this with a concrete application, 3D pose estimation. So in general, pose estimation is an important task for computer vision. For example, you may see some applications of human body pose estimation, okay, from image or videos. So in this case, in this application, we're talking about hand pose, which is even more particular. Most people have hands, and we count on the hands to finish our daily tasks. Right? So if you look at the hand carefully, your hand is an articulated object. Right? So each hand, we can use 21 joint locations. Right, from 0 to 20, right? 21 joint locations. And the 3D hand pose estimation problem is that if I give you a new image, can you estimate the 3D location from a 2D image? Can you estimate the 3D location of the 21 joints at the XYZ space? Okay, this is can easily formulated as a machine learning supervised machine learning problem, because now the input X is a 2-dimensional image, while the output Y is a 21 3D location of the hand joints, key joint locations. In total, the output space is 63 dimension, 21 times 3. Okay. If we formulate this as a supervised learning problem, it's kind of straightforward. Actually, for a human body, 3D human body pose estimation, this is one of the standard ways to train the network. Okay, so you input the image, right? So you first do 2D joint location estimation. You want to locate the 21 joints in the 2D images first, right? And then you can calculate the loss, how good you are doing the 21 2D location detection. And then after you have the 2D detection, we can further improve the 2D heat maps through a 3D regression network and obtain the 3D location of the individual joints. Okay, and then the final 3D hand pose is going to give you a supervised loss, how good your estimated 3D hand pose is when you compare with the ground truth 3D hand pose. Okay, so there are 2 laws. Both of them can be obtained through supervised learning because you have the ground truth. Assuming you have the ground truth, of the 3D hand pose, and of course the 2D hand pose. If you have the 3D hand pose, automatically you're going to have the 2D joint locations as well. So the 3D hand pose is the key to make this learning successful. The more the better, because again, hand is articulated object. There were many different configurations of your fingers, so you may want to use training data to capture enough variations of your hand pose. However, so if you really work into the problem, you're going to realize, although supervised learning looks promising, but when you really work on the problem, you're going to find the problem, the situation is quite different, as you may imagine before. First, the annotation of the 3D hand pose on top of a 2D image is not trivial. Okay, so take this image as an example. This is a 2D image, and this is the 3D hand pose location, human manually annotated. Okay, as you can imagine, even for human beings, there still could be unreliable annotation of the 3D hand pose. You roughly know how the 3D hand pose is, but how do you know the accurate location of the 3D hand joint location in the 3D space? You can only guess. Okay, this is a 2D annotation. This is a 3D annotation, and this is the second row is another example. Okay, so annotating 3D locations on top of 2D images are never easy, and it can be noisy and reliable. Okay, and also different people may annotate differently. It's the same image. If you same hand pose image, if you ask two people to annotate, usually the final results, I mean the 3D hand poses, the annotation will not be the same. And also each single image, you have to annotate 21 joints. Very tedious. It's time consuming, and it could be expensive if you ask the others to help you. And again, one hand is not enough, right? So in order, because of the hand is articulated object, and that we have self-occlusions, that's also a very troublesome part compared with the human body estimation. Hand is much more easier to be self-occluded. Fingers may occlude each other. So that's bring a extra dimension of the challenge when you annotate the 3D hand pose on top of a 2D image. Then, so what's the solution, right? Annotating of the real data becomes very challenging and expensive for the hand pose case. Okay? So the very natural question we'll ask is that, can fake hands help? What do you mean by fake hands? Fake hand is a graphics synthesized hand images. For example, if you want to synthesize the hand, we need to build a 3D mesh, the model of the hand. Then we give the skin to the hand through rendering, texture, and give proper lighting. And then we render the hand image into a background. Then after blending, and this is the eventual image you see. This is a fake one, okay, because the hand is a fake hand. However, today, graphics engine, the rendering, thanks to the very powerful rendering, we can see the fake hands actually look quite realistic. Okay? And then, if that's the case, the very natural question is that, can we utilize the synthesized hand to help train the 3D hand pose estimation of the real hand? So we gave a try actually around 2 years ago. Then we used the fake hands to initialize the visual learning model. Okay, so the advantage again is that for the fake hands, each one of the fake hands, because they're generated from the 3D mesh, automatically we have the accurate ground truth of the hand pose and also the 3D shape, because they're generated from them. So we have the very accurate ground truth, not only in the 3D hand pose, the 21 joint locations, but also even the 3D mesh, the shape. Okay, and then we can use the graph convolutional neural network. Okay? So together with 2D detection, and then while graph convolutional neural network, we try to reconstruct the 3D hand mesh, and then estimate the 3D hand pose once we know the 3D shape of the hand. Okay, the loss function is straightforward. Heat map is the 2D detection, 3D hand pose is the final performance. We also want to estimate the 3D hand shape, so there's a mesh loss here. The mesh is is a little bit more complicated because in order to measure how good is your shape, we try the different types of the losses because we want the hand shape to look natural as possible and less noisy. Okay, but the key message is that here we can fully utilize the full supervised learning scheme because we have enough training data with ground truth. Okay, so we can train the model and then do the regression from the 2D image, and output is eventually a 3D hand pose. A little bit more about the detail of the graph convolutional neural network. Okay, so we tried to use the graph CNN through a coarse-to-fine way. So after we get the latent feature from the 2D detection, we gradually improve the resolution of the 3D mesh until it ends up with more than 1,280 vertices. Okay, and that pretty much can capture the 3D shape of the hand. And once it is done, we will estimate the 3D pose from the shape, which is a much easier job. And there were some steps of graph coarsening. You need to reduce the resolution, and then you need to upsample the features through training. Okay. The supervised learning actually works for the synthetic data, for the fake hands. Okay, and this is the evaluation on the fake hands. Okay, on the synthetic data. The evaluation hands is different from the training, of course, but the performance on the fake hands looks quite promising. Okay, in terms of the mesh error, in terms of post error, this is in the millimeters. Okay, so both of the average error is less than 10 millimeters on average. Okay, this is the absolute physical location error, or on average for the 8.03. That's the average joint location error compared with the golden truth. Okay, and different terms of the mesh loss did help in different ways. Okay. However, when we try to work on the real hands, we still get some challenges, okay, as expected. Again, we train on the synthetic hands. They are fake ones. Okay, for example, the lighting condition is rendered, the skin is rendered, the background is also blurred. Right? And when we apply the same model trained on synthetic hands into the real hands, which has different skin tone, different lighting condition, different backgrounds, we do not obtain a perfect results. The results are reasonable. Okay, so the ground truth is this. This is what the system estimated. Overall, the global structure looks fine, but details are not that good. And particularly the shape. If you look at the shape, it's quite noisy. When we apply the model trained on synthetic hands onto the real hands. Okay. So now the next very natural question is that if there's a gap between fake hands and the real hands, and the system may fail because it never sees real hands, then can we add more real hands to help? But then if that's the case, we need to worry about the annotations, labels of the real hands, because obtaining the 3D hand pose, as I explained already, is not a trivial problem for the real hands. Also the 3D hand shape, right? So how to leverage both synthetic and real data? In this case, both fake hands and the real hands for pose estimation problem. Again, remember our goal is to learn a regression or mapping function from X to Y, where in this particular application, X is the hand pose image and Y is its 3D hand pose or the 3D hand shape. So we're going to utilize the synthetic hand data, the fake data. well, X is the hand image, 2-dimensional, and the Y is the ground truth, which is the 3D hand pose together with the 3D hand pose of the input image X. Okay. Not only that, to improve the generation ability, we're going to feed in real hand data as well. Okay. However, it's different from the synthetic hand data. We realize for the real hand data, we may not have ground truth. That's why the input is X together with Z, not together with Y. Y is the ground truth of the annotations. So for the real hand data, it's easy to get X. Once you have a camera, you can get X. But getting Y, the annotation, the 3D hand pose is difficult. However, there's a auxiliary information from the real hand data we can utilize. So Z here is the depth map. For example, if you have RGBD camera, and simultaneously you can capture the hand in the RGB mode together with the depth mode. So this depth image can serve as auxiliary label for the input image X, although Y is missing, right? And then with the two types of the input, real hand data with incomplete annotation and also synthetic hand data with full annotations. And we want to build a model fx equals to y, where x is a 2D image in the future, a 2D hand image, and y is the 3D hand pose of the hand together with the 3D shape of the hand. Okay. The auxiliary label z, so that's the key information, actually can help a lot to infer the 3D hand pose and the shape in the real hand images. Okay, so here is the way for the weakly supervised 3D hand pose estimation, utilizing both fake hands and also real hands. Okay, so for the fake hands, we can utilize the ground truth from the 3D hand pose, right? And we can encode the output of the 3D hand pose and also the input to the image. And then this is the key step we found quite useful. And we try to synchronize them. The encoder is going to get a feature from both the 3D hand pose, which is the ground truth, and also the 2D image, which is the input. But we synchronize the embedding in the latent feature space by minimizing their KL divergency. Okay, we want after the feature extractor, here is the encoder. After the encoder, the feature distribution of the training data between the input and output, they could be similar to each other. Okay, basically, we're using the encoder 1 to guide or constrain the encoder 2 to extract proper features to represent the 2D image. Okay, after that, we can reconstruct the 3D hand pose and also the depth map. Because we have the depth information from, we can also have the depth map of the hand from the fake hands, right? So we can use the depth map to regularize the performance of the 3D hand pose estimation as well. Okay, and then this part is for the fake hands, which has a full annotation and is a purely supervised approach. And together, we are going to utilize real hands as well. Keep in mind that real hands, we do not have the ground truth of the 3D hand pose. So we're going to estimate, that's the training data. We're going to estimate the 3D hand pose from the real hands, but we do not 100% sure whether this is correct or not. However, similar to the fake hand branch, we can use the depth regularizer, because for the real image, we have both RGB and the depth, right? So we have the depth as the ground truth. So this branch can introduce a loss, but that's the only loss we can utilize for the real images. For the synthetic hand images, we have 1, 2, 3, 4 different losses. The encoder that are going to share, the encoder 2 is shared between the upper part and the lower part, because they are the feature structure from the images, from the 2D images that capture relevant information to estimate the 3D hand pose. Okay, so more losses for the synthesized image. We have 4 loss terms For the real image, we have only one loss term. Of course, we need to balance them a bit to achieve a good performance. Okay, so here is some results we observe. The key column, each different column is a different combination of using the depth localization, which is Z, and also the 2D supervision. 2D supervision means the detection quantity of the joint location in the 2D images, how good you detect them correctly in the 2D image. And this column shows that if we use depth regularization, but not 2D supervision. So if you do not have 3D hand pose system, 3D hand pose as the ground truth, you may not be able to have 2D supervision because you have no idea where is the individual joint locations. You have only the depth map together with RGB. However, with the depth representation, it's interesting to see that it can perform even better when you use 2D supervision, but not depth regularization. And of course, it's going to be better than if you do not have both, right? So if you do not have depth regularization and also you do not know the 2D joint location, and that's purely unsupervised, then the performance is the worst, right? Of course, if you have both, then you can further improve the performance a bit more. Okay. So this is the interesting results, meaning that again, even with synthetic data together with real data, but the incomplete annotation, we still be able to significantly improve the performance. We build a data set for training with synthetic image and also a small one for testing. And here are some quantitative results and compare with the previous approaches as well. As we can see in the synthetic data, we can achieve 8 millimeters as the average error on the real data is worse as expected. Okay, so here are there some visualization results from different data sets. Okay, particularly the first row and the fourth row, they are fake hands. So while the second, third, and the final row, they are real hands, and also the 3D hand pose and shape estimation from the real hand images. More comparisons for the existing methods. Again, by using the synthetic data, it can significantly improve the performance when we compare with the performance which are trained on very limited amount of the real hand images. And here is a video. So I estimate both the 3D hand pose together with the 3D mesh of the hand. So that's why we can see the hand from different angles. And all the results are single image based results. Although you see the video, we do not use we do not utilize any tracking here yet. And this is the hand mesh. Okay. Okay. That's the first part of visual learning with synthetic data.
So for the online attendees, I want to temporarily pause it here, and let me check whether Professor Yuan is with us. No, he is not, because Professor Yuan's video is quite long. So and I would like right now it's scheduled to be the lunch break for everyone. And for the first talk in the afternoon, it's canceled because Professor Harandi has some medical issues. So we will resume back on at 2:40 p.m. PST for the talk given by Professor Zhang Yang last one. And during the lunch break, I will continue playing the talk video from Professor Yuan. If you wish to stay, you can. And after we finish the talk, we will resume at 2:40 p.m. Thank you, everyone.
we do not, in the previous example, we almost do not count on the annotation of the 3D hand pose on the real images. Right? Instead, we use synthetic data to help significantly. Okay, so this part, the second part, what I want to share is how we can do visual learning with the weakly labeled data. Okay, but what does weakly labeled mean? Okay, I want to use another application of weakly supervised activity detection in videos as a case study. Okay, video detection is about detecting a particular predefined activity or action in a video stream. For example, this activity, clear and jerk. So you can see it starts from here, it end up with here. So that's the action detection. We want to recognize the class of the detect action instances in the video stream. Okay. However, the challenge is about annotation. In order to teach the machine what is clear and jerk, you need to provide many training examples. Not only the training videos, right, but also the instances. For example, you have to tell the machine, look, this is start and this is the end, or other part, their backgrounds or the context which are less relevant. Okay. However, doing this is not trivial. So first, even you find a video that contains this training example, you still have to annotate the temporal boundary, where it starts, where it finishes, right, in the video, which can cost you time. Even you can ask people to do this, there's no guarantee the annotation of the start and ending is consistent. Different people may have different opinion of when the activity starts and when the activity is going to finish. Right? Although people tend to be more consistent to tell whether this video contains this action or not. That's the more consistent annotation. But to precisely tell where it starts and where it finishes, it's less consistent. Different people may have different opinions. Okay, so then in this case, the question we're going to ask is that can the weakly labeled video help? Meaning, if I only give you a video and I tell you, look, this video contains the training example, but I do not know precisely where it is or precisely where it starts and where it finishes, can those kind of video or training data still be helpful? Okay. So in order to answer that question, so we need to think about carefully what composes the activity. Activity is the object of temporal structure. Right? For example, this activity contains, we can say this activity, the jumping contains 3 parts, right? The first, the middle, and ending part, the 3 phases, for example. If the activity contains such a temporal structure, is it possible for us to discover it? If we can discover it, then we're going to know when it starts, because we know where the phase 1 starts, and then when the phase 3 finish, we know the activity is going to be done. Okay, without requiring the specific annotation of the boundary of the activity. Okay, so here if we use weakly labeled training data, right? So only video level label will be provided. So we only know whether the video contains the activity or not, but we do not know where it starts and where it finishes, when it finishes. And we also do not know the number of the action instances in the video. If the video is long, it may contain multiple activities. For example, in this case, this video contains at least 2 activities. Right? 1, 2, 3 background, right? 1, 2, 3, and then background. However, the annotation does not tell you this. Okay, the annotation only tells you this video has at least 1 action instances, and then the learning needs to figure out the rest by itself. How to do that? We certainly can model the temporal structure. Okay, for example, if we have the annotation of the phase 1, phase 2, phase 3, imagine that, then we can easily learn the temporal structure using temporal model. In older days, it's a hidden mark model. Today is LSTM, transformer, and so on and so forth. Right. However, the challenge is that we do not know where are the 3 different phases. Okay, we can assume we can learn the filter to help us to identify when each individual phase happens. For example, we can learn 3 different filters. Each one of them is going to detect one of the phases. Okay, and also we have the background phase, the filter, which is also mainly to detect the background part. Okay, if we have the phase detector, filter 1, filter 2, filter 3, again, they're purposed to detect the different phases. Then the problem is also, as I explained, is going to be straightforward, right? For example, using dynamic programming, we can detect the new instances in the video streaming. If we have learned the filters separately, right? And we know for any activity, it is going to have 4 phases, starting from the background. Then phase 1 is starting, phase 2 is the middle, phase 3 is ending, and then go back to background again. So every time along the time, we're going to see the phase changes in a cycle. Okay, that is the pattern of what you're going to observe. However, the challenge is that how can we obtain the filter, the detector, filter 1, filter 2, filter 3? How can we learn that without any annotations or with incomplete annotations? So to address this joint temporal structure discovery and classification problem, or the chicken egg problem, right? So we address it in alternative manner, right? So we first learn the filter and then find the path, the cycle, right? So whenever you have an initial detector, phase 1, phase 2, phase 3, you can run dynamic programming to find the path. And then after that, you collect the new training examples of your phase 1, phase 2, phase 3, and then you can update your detector filter again. We formulate this problem as end-to-end learning problem. Okay, so through a few epochs, we can both discover the temporal structure of the activity together with the phase filters, which can detect separate phases. And gradually, if it's successful, gradually the learning of the phase filter and also the detection of the activity instance can reinforce each other. Okay, so here are some results in terms of the detected, synchronized detection. Okay, the more overlap of the red and the green, because red is one phase and green is another phase, a delayed phase. The more overlap of the two, that means the more the better the temporal structure we have captured, because we did find 2 phases in this example, which are dependent on each other and reflect the temporal structure of the activity. Okay. And not only the temporal structure that matters or of interest, but also if you look at the activity video carefully, we can also separate them in terms of the action and the context, and together with the background. What does it mean? For example, if you look at this activity, green, jumping into the water, right? So green is the real action. The red is the context, what's happened before and what's happened after, right? And the blue is the background, which is completely separate things. And if you look at them in the feature space, you're going to see, although the green corresponds to action, the red actually provides good, the context, the information actually provides good support for the action features, while the blue ones, which are the backgrounds, we should really separate. Okay. So now the question is that, can we, through a weekly supervised learning, can we learn the representation of action and the context, differentiate them in the feature space, and then utilize the learned representation to have better detect the action instances in testing? Okay. For example, it is possible to separate. So it's more like a disentanglement of the feature space. In terms of original feature space, everything are represented together. The action, the context. The context is not necessarily just a temporal context. Even within a single image, there could be spatial context. right? Anything that's directly relevant to the activity, for example, the human body movements, the human behaviors, that's in action. Well, the other relevant or supporting factors, that should go to the context part. Okay, if you do the disentanglement, in this case, we utilize the explicit subspace learning to disentangle the representation of the feature spaces of the video. Then we can separate them into action subspace and the context subspace. Each subspace has its own property, so that we can count on the property to design the loss function and then learn the two subspaces separately, so that each one can serve for its own purpose. And here are some illustrative examples. Right? So this is action video, and the second row is the original feature space. If we do not separate them into action and the context, and here is the separation. So this is the action, the image regions that capture the action, while here are the image regions that capture the context. Okay, and here we do it in the spatial domain, and it can also be applied to the temporal domain. So the context is indeed spatial and temporal. And this is the recent work, so we compare with more recent results. The results are promising. It's the weekly supervised learning performance. It's even comparable to the early days as fully supervised detection results, where the annotation boundaries are provided. Okay, so here comes the final part. Okay, so visual learning with pre-trained model. What pre-trained model mean? If you work on deep learning, I'm sure you understand what I'm talking about. But in reality, this happens more and more in the future, right? So, for example, this GFT 300M is a very big 300 million image dataset used by Google. Okay, they use this dataset to train a image classification model, very successful. However, when people ask, could you share the data due to various reasons, that's very difficult, right? And even it is shared, 300 million, that's a huge amount of data. With a single PC, you may not be able to even handle the data, even though it is public. So then the thing is that, what if the model is released? Okay, instead I share with you the data, because I already trained a model on this data, although it's for image classification only. And maybe my image classification task is different from your image classification task or other tasks you have in mind. But however, the model is already there. We already use a lot of GPU hours to obtain the model. Then the question is that if I want to do something else, not the same task as this model, this trained model is targeting at, can it still be beneficial? How can I utilize the existing model, which is anywhere there, to benefit my own computer vision tasks or data? Okay, so this is the pre-trained model, right? So the model has been released by Google, which is already very kind. There were various ways of utilize existing pre-trained model. Fine-tuning, as many of you already are very familiar with, is just one of the ways. Okay, so here we discuss various use cases in terms of the knowledge transfer, right? In terms of knowledge transfer, or utilizing of the pre-trained model. For example, if you have through knowledge transfer, we know there's a teacher-student network, right? So, for example, your teacher could train on the synthetic data, right? So, and now it's the same task, but I want to apply it to a student network. Okay, this is the same task, but different data set. And we can also have the same task, and also the same data set, but different model. So this is traditionally model compression or knowledge distillation, right? So the purpose is that I have a pre-trained model already. I don't have the data, but I have the pre-trained model, which is trained on a very huge data set. For example, now I want to use a smaller model to mimic the the complicated model on big data set and also fine tune to my own application? How can I learn a better model? Sometimes a compact model. And you could have a different data set and a different task. And also same data set and a different task. Same data set, different task. That is a usually formulated as a multitask training problem. For example, in the same image, autonomous driving scene. However, the teacher is learned for object detection. Okay, already on this particular data set, I already trained our object detection model. Okay, can we utilize this pre-trained model to benefit my other tasks on the same data or on the same scenario, right? So, for example, can the detector benefit my segmentation? My student, my other task is about image segmentation, right? Can we benefit? In this different data set and different tasks, that's the most challenging situation. That's where I have A, B, C together. We have both domain gap, model gap, domain gap, and the task gap. Meaning, the teacher is trained, for example, the teacher is trained for pose estimation, right, on Google. That's one task. Now we want to utilize the pre-trained model, but for different, using a different model first, right? Using a different model and apply to a different data or scenario, and also with a different task. So here, what we want to do is the pedestrian detection, right? So you already train a pose estimation model on a separate data set, and now I want to do pedestrian detection in an autonomous driving scenario. How can I benefit your pre-trained model? Okay, those situations are very common in real applications because we have many different computer vision applications or tasks. Depends on application, depends on the downstream application. So now the question is that how can we utilize the pre-trained model with less labeled data, but to help the tasks you have in mind with as less new training examples as possible. Okay. The way to deal with that, we tried a way of using knowledge transformation through hybrid forward. Okay. That is kind of straightforward. So let's say you have teacher network, right? So you have already, this is a pre-trained model. We're going to utilize that. The teacher is always fixed. So we do not change the teacher. We only change the student. By fixing the teacher, now we co-train the student with another downstream task, right? Which we care about for the student. And then instead of train the student from scratch, we fully utilize the structure and the network trained on the teacher by switch the flow. Okay, so we can switch the student. We initialize the student and we can switch, replace the middle, one of the middle layers with a teacher block, and then we go back. Or we can use a teacher and then we switch to the middle of the student, and then we'll go to the final stage and then go to the task. Okay, by interlacing the teacher and the student and join the training together, we can fully utilize the knowledge the teacher already obtained in his own data set, which could be a very big data set, and also on its own task, which could be different from the task of the student. Okay, this hybrid training, hybrid forward training is different from previous knowledge distribution. For example, usually cares about the same task, but better performance of the student, or sometimes apply to different data domain. And it's also different from the feature mimic because it's also mainly focused on the same task. Okay, so here the hybrid forward can really can transfer tasks from teacher to student because we do not care about really what's the task the teacher is doing. Now with the task the final block. So what we really care about is whether the student, by leveraging the knowledge from the teacher, whether the student can do a better job for the new task or not. That's the training objective. Okay. If you look at the detailed training scheme, there are different types of losses. For example, we can train the input flow can go through this way, right? So go through one student, then go in the middle, go to teacher, and in the final stage, go to student, and then go to the task to get the loss, how good it is. And it can also start from the teacher, and then go to the middle, go to the student, and then finally go to the teacher, and then go to the final task. Or it can go through straightforward to the student. and then get the task loss. The final network, the student network, is the one we really care about, because that's the network we're going to utilize after training. They are all composed by student. Okay. However, loss 1 and the loss 2 are also matter. Okay, also matter because the final during the training, teacher is fixed again. The teacher network is fixed, never change. We use backpropagation to change the student network. This 1, 2, 3, they are all the same student network. Okay, the same network. But the gradient will come from 3 losses together. Loss 1, loss 2, loss 3. They're going to contribute. That's the balancing parameter, because they have different losses. Eventually, we care about only the loss 3, but the gradient is going to be composed by the loss from L1, L2, and 3 together, which is balancing by weight parameter alpha. Okay. And interestingly, we actually see that the blue curve is the student is loss 3. So the blue curve is the normal path, which is the student path. We're going to see the student, by leveraging the teacher, the blue is actually in the middle of the 3 losses. Okay, loss 1 is the worst. That's the biggest loss and the worst performance, because it leveraged less of the teacher. But loss 2 is the orange curve. That's the best performance. Smaller loss and also better accuracy, because it leveraged more teachers. Okay. However, it's interesting. However, the loss 3 is something we only care about, because the student is the one we're going to utilize for the new task. Okay. And here are different comparisons of using the teacher-student for different applications, right? So the first one is about the model compression. It's the same task, but we replace the resonate into a mobile late, which is a much smaller one, and we try to achieve comparable performance as a teacher. Of course, is still worse than the teacher, but it can get closer. Okay. And we can also try combination of the model, domain, or task gaps. For example, the teacher, this one, they work for the same task. It's both of them work on the segmentation task, but the teacher use the ResNet 50, the student use VGG, and they also use different training data set to fine tune the student. Okay, and you can see the performance improvement. And this one is about the same data set. They do not have domain gap. The teacher and student, they work on the same data, but using different models, right? And also for different tasks. One is fastest RCN for detection, and another, the student is deep lab for the segmentation. And we also can see the beneficial of the combination of the tasks. Although the task is different of the student, but still we can learn certain knowledge from the teacher. And this is the balancing parameter alpha. They change over time, become smaller. And the final experiment is the most challenging situation, where we consider the gap of all of the factors. Model is different, domain, data is different, task is also different. For example, the teacher work on ResNet for human pose estimation, and the student using mobile net for pedestrian detection, and they work on different data set. And we also see the beneficial. Without the teacher, the student cannot do a good job. The student will do a worse job. Okay, meaning, but the student can still leverage the teacher, even though the teacher works on a different task, although it's a relevant task. Okay, so I think here comes the summary of the talk. Okay, learning from less labeled data. So just a quick summary. So today we briefly talked 3 different possibilities to help you learn from data when you do not have enough annotations. Okay, first, you can think about whether you can fake some data, synthetic data, for the hand or human body, or anything that can use a graphic model to synthesize. That could be one alternative. right? Because the advantage is because first you can create much more data, right? At least for pre-training, and also you can control the diversity of the training data. Sometimes the real data is big, but it still could be biased, right? So it does not have, it is not diverse enough of the real data. Then it could be still not good enough for you to train a model. And also that's the favorite part I really like for the synthetic data, because usually it can have accurate ground truth. Okay, so annotation is one thing. Accurate annotation, that's another thing. It's actually a completely different thing. In many of the situations, if the annotation is not accurate enough, eventually there will be a bottleneck for performance. Second, we can also do visual learning with weak labeled data. Okay, the advantage is not just to save the annotation cost. Okay, if the weakly labeled data works successfully for your application, that usually means the learning procedure is kind of self-supervised or discover the pattern within the data, no matter it's temporal structure pattern or spatial pattern or the feature pattern, because you do not have the annotation, so you have to push the algorithm to figure it by itself. Usually, this could, if it can perform very good enough in the training data, it may bring better generation ability. Okay, then that could benefit for your future applications. Okay, so that's the thing. And sometimes we have no choice, but we do not have fully annotated data. So in that sense, we have to try our best to utilize the weakly labeled data. And finally, we talk about visual learning with pre-trained model, which is a very common situation we're facing today. Every paper, many papers actually release their model. Okay, so we publish a paper in CPR WSCV, we release the paper, we release the code, sometimes not the data, but the model, right? And then those model, think about that, they have been already trained many GPU hours, a lot of human efforts on a big data set. So they are there anyway, right? So, but how can it benefit to overall tasks? That's really something we should think carefully, and so that it can help us to save the cost or the time to annotate real data for over a particular task. Okay, if it can be successful, right? So using pre-trained models, we can leverage previous efforts of data collection and also model training, right? And even though your new task is different from your pre-trained model, there are still different ways. I think this is just what we need as a community. So we hope this pre-trained model can benefit other different vision tasks and the different data as well, data domain as well. Okay, so this is the last slide of the talk. Why now? I'll go back to share the thought why we want to learn from less labeled data. Right? In the first few slides, I already shared the key of the role of the big data in today's visual learning. Right? So we believe more labeled data is going to give us better performance. Then if we ask the question about ourselves, what essentially we want to do to learn from less labeled data, because more labeled data can give us better performance, but why we should learn from less labeled data is just because we want to save the annotation cost. That's just one of the reasons, but I don't think is even the key reasons. Right? I think one of the motivations that we may think about how we can learn from less labeled data is because although more data can give us better performance, but that's only for one particular task. For example, if you want to do face recognition, you need to collect millions of the faces, and you can do very well for face recognition. However, if you change a different task, what do you have to do? If you believe in more data, more labeled data, it will give you better performance, then you have to scratch from data collection for your new task. If that's car detection, you have to collect millions of the cars, and then you can do a better car detector. And then another task, you have to collect the data again. Okay, so we have so many vision tasks. The number of the vision tasks is also growing. Not only the performance of the individual task, we see better face recognition, better pedestrian detection nowadays. But the better we can complete one task, the more we're going to see other computer vision tasks, because people tend to believe it's going to work. And then the ideal case, if that's the scenario, if you put your scope not just one individual computer vision task, but a family of computer vision tasks, as a human can do it very well. As a human being, automatically we can achieve different computer vision tasks. Maybe we're learning it together, maybe we're learning it separately, maybe we're learning it in order. But the one thing I think is clear is that we do not count on huge amount of data when we try to acquire a new computer vision skill, or we try to complete a different vision task. We do not have to count on a huge amount of the labeled data as a human being. Okay, so the thing we actually want is that we want to a mechanism or a scheme or a framework that can help us to complete multiple computer vision tasks, right? Either in an incremental way or in a batch way, and count on less annotated data for each individual task, while we still can get a good performance. But I think we believe that is the goal. Actually, as a community, we may want to pursue together. Okay, so that is the end of the talk, and I would like to welcome if you have any questions. Thank you.
All right. Since the first talk in the afternoon at 2 p.m. has been canceled, we will resume the workshop at 2:40 p.m. Pacific time. So see you all at that time. Thanks.